Okay, welcome. Sorry, I was a bit late, but it's still starting around about close to 2 o'clock. Um, what are we up to today? Um, Essentially, what we want to do is we want to design a system. Last time we heard that for communication, there was a principal concept that, at least for radio communication, we use a certain frequency as our channel. Shannon told us that we need some bandwidth around this channel, so let's say 2 gigahertz. So we take something like, for this, we take a couple of megahertz around 2 gigahertz to make that happen. Why do we those frequencies selective? If we transport information, and that's true also for sensing signals, so for example, if we had some sensor, a radar, for example, the general behavior, for example, of the atmosphere, but more likely the geometries, is extremely frequency dependent. Yeah? So anything we do works over frequency. So what we want to know is, first of all, at a specific frequency going through such a channel, what do we do? Yeah, so that's the first idea. And this can have a couple of items. So for example, the first idea you could think of is to have free space. And why is free space frequency dependent? There are some easy things which you know already without ever having visited a lecture on microelectronics or RF. Yeah? So for example, you know that very low frequency waves, they don't see this building. Kilohertz transmission, which can be radio already, just goes over the IMTAC. The IMTAC is way too small to see this excessive band, this excessive wavelength, because kilohertz is kilometers of wavelength, so this building is just small. Yeah? And what makes RF now interesting is that the structures which we talk about are in the range of the wavelength we use. Yeah? And I gave you this example. For example, there is some relation between a geometry and a wavelength. And you could say, is this new? And the answer is no, because you know that a large musical instrument gives a deeper sound, a longer wavelength. That's something you have known forever. It's not new. Yeah? So there's apparently some resonance between this wavelength and the geometry. And why is this important now? The importance is that when we go to a specific wavelength or a specific frequency, then we know what to do with the channel we go through. Now the question was, I think we talked about this the previous lecture, is that why do we speak about frequencies and not about wavelengths? That's something we clarified already, because frequency, we learned, is independent from the medium. Yeah? So anybody of you, if you are not from India, from Germany, Deutsche Telekom definitely buys frequencies. China Telecom buys frequencies. Indian Telecom buys frequencies. They never bought wavelength. And the reason is that you know very well that inside, once we are transporting through a channel, we go through media. So the open air is quite simple, because the open air is essentially vacuum, because the index of refraction, which modifies the wavelengths and makes it typically smaller than in open air, that is something which we know about. And for example, here the wavelength for 2 gigahertz is typically in the range of, so 3 gigahertz is a decimeter. And once this 3 gigahertz waves goes into a chip, then the wavelength is transported by square root of the index of refraction, which is typically for materials like plastics or anything which we would use. Semiconductors, for example, would be in the range of 10. Yeah, so square root of 10 is roughly 3. So the decimeter wave inside the chip goes to 3 centimeters. Yeah? So that is the idea of a channel going through. But what we want to know over this channel is that what happens frequency specific. So we talk about something, we say there's a frequency, and for example, for one frequency, we know how to get through that channel. Yeah? This is a very fundamental idea. You can think it, we started with something very simple, which is this inductor on the right, lower right. But even this is already not so easy, because even this thing, which turns out to be an inductor, if you look more closely, this is not just an inductor. Yeah? This at least has some derivations from this principal idea. However, the concept we use is quite useful. So you say whatever it is, it has a behavior which is described, in this case, mainly inductive, modified by some maybe capacitive behavior and by some losses. Yeah? But it's kind of a block. And this block can be described when you put some energy to it, or better power, and you put it to the ports of this device. So you say there's an input and an output, and you just probe this input, output at this frequency. Yeah. Then you, just to make sure it's running, then you are sure that you have some idea about what this thing is going to do. And in the easy case, this inductor will mainly be inductive. So we still have some clue what it would do. But when you go away now from this principal idea of a component, you can start building combinations of that. So for example, you see a chip has maybe many inductors and some other components. So we're searching for a way in the frequency domain to analyze such a system. The chip is already considered a system of individual items. And this method is extremely powerful. That's why I'm telling it to you. So it's not about a single inductor or a chip. It's this idea how we combine things. Yeah? And why on earth would you want to do that? That's something you see here. This is a chipset which we can still open and see. This is the iPhone 5 chip. I know it's history, but it's just to say it is a relatively complex matter already. So it has billions of transistors, and we are trying to analyze that now. Yeah, so and what we want to do is many things. So if we have millions or even billions of transistors, how do we put that together? The first learning from a simple approximation was, you know that this system here is built by around 1,000 engineers, and they definitely are not going to build this in sequence, in serial. They will run in parallel. Yeah? So we need ways, and this is these interfaces of chips and other items that where we learn how to communicate an interface. So we say, this group is designing part of the chip lower right. This group is designing lower left. You are responsible for the amps, which are on the top left, and so on. Yeah, and we learn to interface that. And even within our problem, which you are not solving together, let's assume you are representing 200 engineers working on something like that. Even within that, you have to shut it down. So you can take it down to an individual function, which at some point will guide you to the level of components. So at some point, you will start to understand, okay, this is now a transistor, or this is now a passive, this is a line, this is a resistor, or whatever. Yeah? And you're starting to understand, okay, this makes some sense in the cooperation aspect, and there's a strong need to talk about interfaces. Yeah? And one way in the system theory to go through that is this idea, when we go now to the analysis what we could do to do that. I told you last time we can all the time. These representations are never unique, so you could look at this from these waves of power, which I'm suggesting. And the reason why I'm suggesting this is that it's relatively easy. We learned already last time that representing measuring power is something we can relatively nicely do. But if we have to go to the full understanding via voltages and currents at this point, it might be from a perspective relatively complex. Yeah, so that's something which makes your life a bit easier from the point of view where how you're approaching this this problem. And what we introduce is these complex wave parameters, and they're essentially power. So what you're defining is you're sending the idea is always you're sending waves. The A1 waves are the incoming waves at input and output, and the B waves are the reflected ones. Yeah, or as it's not just reflection, there's also something which goes through the system. For example, hopefully, for example, in an amplifier, you hope that A1, a signal which is incoming, then a part of that will be really going into the system, and you hope that this fraction of the power you offered is amplified, so that the B1 wave, the B2 wave leaving the device is not as a higher level than the one which you offered. But there's also this information that you can look at this problem from the perspective that you say, not everything which I'm sending out to leave the device is actually coming out of the whole system or will go into the next component, because there might again be a reflection at the next level. Yeah? In this case, this would be represented by the B1 wave of the next device, and then because there's nothing in between, it would come back as the A2 wave into the device. So effectively your output would not be B2, but it would be something like B2 square minus A2 square. So this would be the effective power which would be transmitted. Yeah? And the idea is quite clear that with this concept, we are suddenly subdividing the system into something we can manage. Yeah? And what we are avoiding is a description in this complex system that you say we have to go into voltages and currents in detail to understand the full system. And what we then do is, when we are composing now this from multiple systems or multiple components, that we have millions of such matrices which send us through the system and help us to understand what we are really doing when for example, we are offering components and combinations of components to influence our channel path. You know? And that sounds like it's not really much what we are doing, but it's comparable, simple. It's a relatively simple idea. There's a couple of things where we have to be a bit careful when we make such an approximation. And I'm saying, call that here the independence of the elements. And for example, there's one critical problem which we have is that when we attribute such a component to a system or a matrix, we are defining some interfaces. For example, we say, for example, that at this port here, we are saying that the component really ends. This is our interface. However, when you think this from a wave perspective, this is, I'm an idiot. This is nonsense, because I told you maybe in the first lectures already, a wave never stops. Yeah, so how can I say that the representation of this element is stopping here? And that's critical, because you say a wave could go on. And we hope it's going on, but in the description of what this component does, we have to be careful, because, for example, if you have such a chip, what is a typical thing we are optimizing in chip design? What is a parameter apart from the performance? What are we always trying to do from your experience? Power, yeah, but if you're designing a chip, so you have a solution and then somebody comes and says, this is not good enough, make it better. What would she or he ask you for to do? Same function, but?
Small space.
Yeah, this is something it's built in our, very good, it's built in our mindset. So we want to do the same, but we want to make it more compact. Yeah? But what you're doing then, if you look at this description of the network, you're pushing it together. Yeah? And then at some point, how do you make sure, for example, that if you have the two lower inductances, this and this, if you shrink them in space, how do you make sure that they're not coupling? So this is really an independent description from its block diagram. Yeah? So if you make them too close, they're starting to talk to each other, which means on a mathematical level is that you, from this perspective again, that you, that the representation of this component is modified because this is just a matrix. Yeah? And the matrix now suddenly starts to depend on whether there is a neighbor or not. And this is a bit shaky if you go into this sequential thing. Yeah? So this is something we have to somehow consider. Still, the system works. We just have to account for exactly this effect. This can be done. So the idea which I'm trying to impose is now that we are now going through a sequence of components. And when you are at one frequency, assuming for a moment that makes sense, yeah, then we are starting to connect multiple components. And the analysis which I'm presenting now is a generalized way of saying how to offer something to a cable, could also be a transistor, a satellite system, to be influenced by the outside world. Yeah, so what you say then is, there is something we want to understand. Now we are asking ourselves in terms of power waves, what do we have to offer, and what is coming out. Yeah? And if you ask yourself, what is this power wave? The power wave, for example, is the TV signal which comes out of the transceiver, which should go into the next, maybe into the TV itself. There's a connection. Yeah? And the generalized analysis is that you are offering some power, and the idea which comes along with this concept is that power is always offered, no matter what you realize. Power is absolute, but it's offered with some impedance. And that is always something, this impedance idea is always a bit tricky, because when we are sending even something through space, so we don't even have to consider a plug, and so we don't need that. The power we're getting from the free air or from the free vacuum comes at an impedance. And this impedance is, we derive it in the other lecture, is 120 ohms. So this thing, which I cannot really catch, has an impedance. Power which we get always comes at an impedance. In a cable, if you take that, it's more understandable. So there's waves and there's voltages and currents on there, but the exact looking of this component defines also some impedance. Yeah, that's something we have to accept for the moment. I will justify that again later. So the only thing that you say, power, it comes, voltages and currents come, but you saw the relation between voltages and currents is defined by a reference impedance. Yeah? And if you find that odd, you are right, but it's also not a big problem, because I told you last time already, when you go to MediaMarkt and have a 75 ohms output, Intuition told you buy a 75 ohm cable. Yeah? So that's not really something you found crazy in your life so far. But what generally means is that when you have that concept, there can also be impedances which have other values, and they can even be complex. That's a bit of a strange concept. Why is this important now? This parameter is effectively defining our cooperation. So the lines between you and you and you is the level of impedance. Yeah? And for example, we can always take that from a very simple idea. If this cable has a power wave traveling up, what do we expect if there's nothing connected? We expect a total reflection. Yeah, because nothing is essentially leaving this cable if it's not connected. And the power concept is quite useful then, because you say power has to be conserved. So it either leaves the cable or it goes back. Yeah? And why this is now also a good intuition, because the power cabling tells you, well, what kind of reflection is that? And the idea is that the reflection, which when we're sending something out to the next component, yeah, there is not just the value in ohms, which represents this impedance, but there's also a phase. Phase critical. But think about it. When you get your power back, it can be still with the same phase, so the wave is traveling, and then it is reflected. And you can have that with zero phase, so it just comes back. You can also have it with any other phase. Yeah? And for example, there's a physics experiment which you may have done in your life. This is a kind of open cable, so there's nothing leaving the cable. If you short circuit that, there's also a total reflection because still nothing is leaving the cable, but the phase will be different. And if you have seen any wave experience in your life, there was, for example, the experiment, you might have thought there's a physics experiment where you have two conductors, and there was this idea that it's either they're even ending, or you can short circuit them at this end of this traveling wave on these two cables. And if you put some metal piece on top, the situation is still the same. Nothing can go beyond. But there's of course a difference whether you keep the cable open or whether you short circuit it. This is total reflection, but it's coming at a different phase. Because in one case, and the current perspective is useful. In one way, you have maximum current there, and in the other case, you have no current there from this wave. So there you start to understand there is a possibility that there's different phases. That is something which you might have hit in your physics life before, that this is a useful concept in the sense that not only power is to be reflected, but also phase. And this can be generalized. So this is this idea, and if you're not convinced, connecting things, okay. But what we then start to do is, when we have impedances, for example, this generator here, and some kind of impedance, there's power coming out, and I want to know how much will effectively now enter at this frequency into the next component. Let's remind ourselves from the understanding why we talk about this. So when we talk about these impedances, we have some things which are quite easy. So for example, there's the ohmic resistance, which has impedance which is just real. Yeah? But it's not really rocket science to understand that some other effects like capacitance and inductor, that they have something which is frequency dependent and an imaginary number. Yeah? So this is something I think we saw before. So apparently there's some frequency dependence of this reflectance. And second, there is also a phase, because the moment when you have this I in the impedance, you're starting to get reflections which are just not phaseless. Yeah, so that's just why this general problem is useful. And now, under these considerations, we now go through the system. So we're sending a power wave out. Then what can happen at the first port? A part can be reflected, and there can be some phase to it, and this we represent then in either a complex reflection coefficient, or we just say, okay, we say we are representing it by this matrix, which is the equivalence. Yeah? And what you do then is, when you're sending something out, multiply by a matrix, and then you will know what is going into the next. And this next here is represented by, in this case, by a load, where we say there's another impedance again offered. Yeah? So you're multiplying yourself through the system, and it's not just this representation which is critical, it's the idea how you get yourself through the system. Yeah? The only thing you really have to accept is that everything which we want to do in such a component can be represented by capacitors, inductors, and some resistance. That is the only thing which we know about. Yeah? So let's make some easy examples. So for example, if we have a 50 ohm cable and we connect it to an inductor, what would happen here at this interface? Keep it simple. Let's assume you have something which is essentially inductive, and you have a real impedance hitting that. What do you think would happen? What are your guesses? Yeah, very good. And more specifically, why would there be reflection? Yeah, what would be the real part of this? If it's inductive? Very good. Yeah. So there's apparently from the 50 ohms to the 0 ohms in the real part, there's apparently already a difference. Yeah? And then why would there be a phase? How, first of all, what would determine that phase? So the frequency where we are at, yeah? So that's very good. And now if we go to, can there be a match between a real impedance and an inductor? That's obvious, yeah. So that over there you're starting to feel, what's going wrong here? Because we are trying to make a real number consistent to an imaginary number. So that is already a problem, yeah. And now the condition which we are deriving from that is now going through the system, and we are requiring now a condition where we say how to send what would we need as the next component to match that. You could also say we are maximizing the gain of the system in the middle, whatever gain is, or don't make it too complex at the moment. We are minimizing the loss. Yeah, and this is something which is a learning now. If you have never seen this idea, what can go wrong if you have a real cable? Let's assume you have two connectors coming in here, getting out here. So assume there's a second collector here. Now you're sending in a wave. What can happen? First thing is what happens here. There can be, we said that already, reflection. What happens to the energy power which goes into the cable? What can happen to that?
You can damp.
It's very good. Yeah, so a passive device will typically damp it. Yeah? And it's a good day to explain that. Typically with increasing frequency, this damping will increase. Same as rainy weather will increase the added frequency, will also increase the attenuation in the atmosphere. And if we, especially today, if we go to higher frequencies, this attenuation will increase strongly. Yeah, so this is always the same idea. So there's damping. Yeah? And this damping we cannot really kill. We cannot make the cable less damping. That's important. And then there's the next idea. Let's assume this is the output now. When we leave this cable, we can still lose something. Because if it leaves the cable and there's again a mismatch, then we can lose something. Yeah? So we have two conditions here. So even if you are through with the input, it's not clear that it's leaving it at the output. Yeah? And now if you want to maximize from generator 1 to the next component, the load, if you maximize, you can go through a procedure and just run a simple second order optimization. This is what is depicted here. So you go through the system, and what you are asking is, there's the reflection coefficients at these two interfaces, just to say what it is. This is this, at this point, what is the reflection there and there, and how do they have to relate to the input impedance and the output impedance? You can ask now, why is he asking that question? The answer is because this behavior will tell you what the system will do at this frequency. There's not more. That is why this system is so useful, because once you know that at this point, at a given property of the component, you know what the system is doing. Yeah? And in a simple cable, you ask how do I minimize losses here at this reflection? How do I minimize here at a given loss in the cable? Now, we are going through these systems. That is just assuming you're stepping through that. That's all which is written down here. and you're sequentially going to the end, and what you're ending up with is essentially you're representing the reflection coefficients which you have there by these measured matrices. This is a bit of calculation, yeah. So you say essentially the input reflection will first of all be influenced by this S parameter of the component. That is not really difficult because there will be a reflection when we hit that, but there's also some contribution when you look at the first graph, which is related to what's happening inside the device. Even coming to the point that the reflection here, I think I have to show it here, that this reflection here is not only influenced by what's happening here, but also what is happening inside the device and what's happening here. That's why there is a dependence. Yeah? So you're going into the system and the system reacts fully. Yeah? And the same you do when you look at this analysis, you write it up when you go to look at it from the output. And then based on this writing, I optimize the power going through the system, which is essentially the powers which we send through the system, and now we have to make some definitions. So essentially what we are interested in is that this power at step L is maximized. That's what we want to do. So you have an input power. The three parameters are these the ratios of the RS is typically fixed. You say how should R1 be, and then when the device is leaving, how should R2 be in relation to RL. That's the idea. Yeah? And then you're multiplying yourself through the system. And what you get then is the transducer gain, which is now not just, the idea is not, there is a gain of the component itself, which is this damping. So you will have always a bit of loss, as you correctly said. But it's of course also dependent what this reflection is here and what is at the output. So you can, it's like, and I think it's a good understanding, like a car, you can run an engine at max power, but if there's no clutch connected, there's no output. Yeah, so you're pushing the pedal real strong, the engine is running, but there's no transmission. And that's exactly why you have this deponent both on the input and at the output. So there needs to be a connection. And it's of course clear if this gain is maximized if you do some things right. Yeah? And then, to cut a long story short, you're coming to the point that at this particular frequency, you're coming to something which you kind of knew. And so because the RS has to be the conjugate complex match of the R1, and the load reflection coefficient has to be the conjugate complex of the R2. Where did you know this? I didn't tell you, but as I said, in a MediaMarkt experiment, 75 ohms, you would have bought the 75 ohm cable. Perfect match. Does it match the condition? Yes. Why? Because it's a real number, and the real number is the conjugate complex of itself. So that's no problem. So that apparently fits. The new thing is that when you have this phase consideration now, that you need to compensate any real part, any imaginary part by its opposite. So for example, if you have an output which is not just a real number, but for example, if I'm generating this output at a certain level, 50 ohms plus I 50 ohms, so the next thing has to be 50 ohms minus I 50 ohms to make it matching. So then we have maximum power transmission here. And then the next step is same at the output. So that then overall, if you have no reflections at input and output, the guiding loss will be the loss of the cable. That's very simple. So no matter if the matching is good, then you have a perfect match. And the only loss you have through that system is the loss you get in the cable, which is physical and cannot be avoided. The next thing is to understand why do we do this fuss with the phase and the frequency dependence. That has to do with this idea that we are representing everything on this planet by this description. So we say it can either be resistive, capacitive, or inductive. That is a bit hard to accept. And there's only one case where this is not sufficient. If you think, for example, of an amplifier, there this is useful, but what is missing in this description? There's something missing which we definitely want for electronics. So there's resistance, capacitance, and inductance. This is nice. But what are these, if you compare, I mentioned already active and passive before, what are all these components which we are representing here? They are all, yeah. And as long as you're passive, this is the full world. Yeah. If we are going active, we need something in addition. It's just some elements in this description which essentially lift up both the magnitude and also modify the phase in an active way. Yeah, that's something we have to add at some point, but this is quite easy. That's not the real problem we have, but it's just to accept that by some representation like that, we can do that. We had this problem, by the way, already, because how was this attenuation described in here? We were discussing so far the interfaces, but somehow you said fully correct that this cable is damping. Yeah? And the same you can also, so this is a reduction of the power, but in an active component you also increase the power. This is what you do from a conceptual point of view. Whether this wave is slightly going down or whether you ramp it up, that's not really a difference. It's just another factor which modifies the idea. Yeah? Good. So this is so far an idea which is quite useful. And the idea is now, when we are starting to look at now something more interesting than a cable, what have we learned? The first thing is what we have learned is that when we go through such a system, we can, for each frequency, we can make that analysis. And if it's all the interesting frequencies we have, then we already have described the system. So we will know how to transpire through a channel. Yeah? And I said explicitly that even the atmosphere is included in this consideration. So it is something that we just multiply. So for example, you're catching, for example, I'm receiving a signal which is sent out on top of there. There's a little bit of channel which goes through the atmosphere, a little bit of damping. Then there's a mismatch with the antenna taking me inside the chip. Then there's various chip transitions. And at some point, I'm getting into the processing unit. And all this channel description is there. Just to give you a feeling why we are talking about this, yeah? And why is it useful to have a frequency dependence? I also mentioned that already last time. You're building this cell phone to operate at some frequency with some bandwidth to receive, but you're also building it to reject certain things. So you definitely want some other signals not to enter your transceiver. Right? So some things you simply want to be kept out. Yeah. For example, if you're transmitting at UMTS, you simply don't want the signals coming in as GSM. So you will build it in this way that frequency selective, some signals are taken in, some others are rejected. Yeah? So the idea that there can be a full rejection of a signal is quite useful. Yeah? It's not out of the world. Yeah? And what I'm now, so this is radio communication, okay, but this concept is much more useful, if you start thinking in this way, what all the things are which we have in electronics which we need to talk about. Yeah? So let's assume we are talking about radios. So I told you 2 gigahertz is specifically radio. But now let's talk a little bit about some things which you might have encountered in your life, independent from RF. So no RF. So for example, we're coming to a microprocessor. Yeah? And just to mention it, if we open this thing and we look at the microprocessor, what are interesting frequencies which are in this digital system now? So which things are in there? What is a frequency when you, for example, look at your microprocessor? What is a frequency you would look at?
Clock speed.
And what is a typical clock speed of something which we have here? And why is it so high? Does this have to do anything with radio communication? The simple answer when you first started it, no. Because the microprocessor also would work at megahertz. Yeah? So this clocking and all the things you do works essentially at any frequency. Yeah? So this is not specific. The only reason why we increased that high-speed digital design is because you want faster videos, you want to look at faster memories, and so on. However, you cannot tell physics if it's radio, work this way, and if it's digital, forget your rules. That's not useful. Yeah? So apparently, the system, the clock frequency of a microprocessor is also a wave. If I had asked you at the beginning of the lecture, the signal going from the memory into the microprocessor, what is that? You would have said this is a current switched on and off. Unfortunately, it's operating at the same principles. Yeah, so what you're doing is when you're exchanging digital signals on a board, you are sending away packages of waves. So this principle, which has, first of all, nothing to do with radio communication, it's the same idea. So what I showed you here, this is a microchip. Sorry. Let's show you this. This is a microchip, and this is obviously, you have to study the size. This is 2 millimeter by 3 millimeters. So this is a really huge device in terms of digital standards. Yeah? So this is huge. And why are these radio frequency things huge? Because the elements as I told you with the music instruments, they have to be somehow in the range of the wavelength. Yeah, so this is why this electronics, if we design it for radios, it's always related to the external size of the component. Yeah. So again, like in the instrument, you have a big instrument, you get a deep sound. The same is here. You keep the chip big because things like that will not work if they are too small, because the function of the component is always in relation to the wavelength inside the chip. This is intentional. Now in the digital chip, you say, oh, I have to clock very fast, and suddenly you realize, oh my God, this is a radio wave, which I'm sending back and forth. Yeah? And what I'm telling you, although you're not intending to do, you're suddenly stuck with these problems, because whether the buffer of a microprocessor, in this case, for example, is accepting the wave, cannot be totally independent from what it's seeing. So what I'm trying to say is, you didn't build the buffer at a certain impedance level, but if you mess it up, then it will not work, because if you're sending out a digital signal and it faces the next component, and you're going back to what you just learned, if at this frequency you have a total mismatch, the digital signal will not go into the next component. Yeah? The digital design phrases this a bit differently, however, it's the same problem. And this is very important, that we only have one world. There's only the time domain world and the frequency domain world, it's the same. The trick is, if you build something like that, from which perspective do I approach it to make it easier in the understanding? Yeah? And for example, it's very difficult to say I have a digital signal which I'm sending out. I'm sitting there, what on earth will happen if it hits this new component? But from what you just learned, okay, somehow you determine the impedance of component 1 and of component 2, and you get some clue what's going to happen. So this is how you design systems. You just look at it from the right perspective and you understand what it's going to do. Yeah. So this is where you really say digital, RF, analog, doesn't matter. You just choose what is best for you to understand the system. And so there's no X, Y versus that. It's just you take either. Yeah. And that's what we call then mixed signal design. We just take what we need to understand the system. Okay. The next thing is now, we have now some reaction of the system. So apparently this cable does something for us. Yeah, so it's just transpiring the energy and the power, and we'll have some mismatch. Yeah? What is also included in this concept, that is something which you also kind of know. When we are now going through all these things which we are describing as a behavior of something, there's certainly some things which are definitely in the system. So for example, you said this cable has a property, and the property is it will damp. So this is built in. This is not just what we do. It is built in this cable. There may be other cables who have more loss or less loss or different phase behavior, but it's something which is in this thing included, like the damping. Yeah? And the same idea is, so no matter how we describe that, this cable will always, we will always lose 10% at this frequency. This is a property, and we call that property, and in system engineering we call that an invariant, because no matter how we describe it, at the end of the day, the power will go through and we will lose 10%. Yeah? And the same is true here also for the when we go now a bit active to make it a bit more interesting. So first of all, we want to interpret what we're getting there in this system approach. Yeah? So it's not just that we say this is some mathematical description and it's not understandable, but some things are real. For example, why does this cable, for example, have losses? What would you say then? What is the easiest way why this cable has a loss to understand it? What would you say?
Resistive losses.
Yeah, very important. So in any what we call, later we'll call a waveguide, that all these metals in there have a resistance. Yeah? And that means if the cable is longer, we will lose more of the power, very correctly. Yeah? And also in a positive way, for example, when you have now an active component, a transistor, or an amplifier even, then we will know this thing will amplify this at a certain level. Yeah, so for example, if we have an input signal of 1, whatever the unit is, and an output signal of 10, and we know this thing is amplifying at this frequency by 10 dB, which is something which is a property. So you buy a transistor, and if you need 20 dB of amplification, you just buy another transistor, which has this property. So this is not crazy stuff, it's just very real. Yeah? And also, when we are looking now at these descriptions we are looking at, there has to be also some kind of interpretable quantities. Yeah? So for example, we saw that this inductor was essentially an inductance. Yeah? So if you build a big coil, you will not be surprised that this thing has inductance. Yeah? Same if you have a big capacitor which you build, you will not be surprised that this S matrix, which we talked about, has mainly capacitive elements. And the question is now, this was something, there's no real preference how we describe the system in the theory. There could be any description for that. But what I'm trying to imply is that certain things are simply, you could also go look at the same thing also, as I said, with voltages and currents. This is all perfectly equivalent. However, it's not easy to manage that, because when you are speaking about a channel, as we started the lecture with, we are not really interested on the planet. If you're Netflix, which you want to listen to, you will never consider in the meantime whether there was a voltage of 20 volts when this Netflix signal was transpired from station A to station B. This is totally uninteresting. Yeah? The only thing is to know, going through the channel, that enough power goes to the next level, and then at certain point you will receive your Netflix signal at a decent signal to noise ratio, so that you can still see the video. Yeah, so that is the idea we are going through. So there is a preference from the simplicity of the description, not from the general idea. Yeah? And the way now how to approach things is that's what we are doing when we are designing such things. We are taking things which you can also receive. Yeah. So for example, if you have such a cable, what can you do? You can now start to take all the properties. You can start to think about voltages, but you can also at some point decide on the system level, the only thing what this cable is doing at this frequency is I'm sending in some power, I will get this reflection, and there will be this output, and there will be this reflection at the output. Yeah? And this is exactly the way how we create the data we later need for example, some kind of complex design. We just say, okay, we have a device in the middle, and we just, whatever it is, yeah, you can go perfectly blind. You're not questioning anything, you're just putting it to some setup, put it between two couplers, and measure these incoming and outgoing waves. Perfectly behavioral. Just what does it do? It's not what it is. Tell me what it does. And that is a very good abstraction level. Of course, at some point you have to think a little bit. For example, if it's just a cable, you don't mind. But if you have a transistor, you need to account for certain things. For example, a transistor needs some DC power. Yeah? So for example, in this case, these ISTs, which are essentially low frequency filters, they will supply in addition also some DC current to the device under investigation so that the transistor turns active when it's probed. Yeah? So this is the lower part. The rest is just an intelligent way of sending at certain frequencies waves to the device and measure the reflection. And you can say, why? Because what will you create with that? You will create components or descriptions of components which can be relatively complex. Yeah? So what I'm trying to say here is this idea. As long as it's simple as that, it's relatively simple to say what it does. Yeah, so you can say there's an inductor, and it will be mainly an inductance. And you might even be able, from some approximations, to calculate what this thing will be doing. Yeah? However, there might also be some other things which we have no clue about what it's going to do. Yeah? So, for example, just a very simple idea. You have one wave coming on a waveguide, so on a line, and you just want to separate it into two signals. So suddenly you are in a problem, there's a geometry, and what's going to happen? Of course, you can also make some sense into it, but there's a very general relation between the geometry and what it does. And if you have no clue, if it's unknown and you don't have the description, you can just take that approximation and just find out. Because as long as it's a component which you can somehow send a wave to, you will find out what it does. Good. Just to say what this testing thing does. So one idea is that we do all this data processing in this case independent from the frequency, and the only thing we change is that we are going through the frequency with a synthesizer. So the source of the high frequency signal will just run up at the frequency which you want to look at, and you will send these waves. Yeah? And then the processing of the information which is in this test set is just down converted in the sense of this heterodyne approach we had already, that we take it some frequency where it's very easy to look at. So the effective analysis is only done at some very low frequency. So you don't have to think about gigahertz. You do this at 20 megahertz. So this is also an idea. And you just run through the system at each frequency, you down convert, and then you get the information you want on these reflection coefficients. And so that makes also our life in the measurements a lot easier. And let's now start with something which is a bit more attractive in the understanding. Yeah? The nature has a lot more things in it than we would know from the beginning. Yeah? And for example, there's some active amplification now, where you can say, when you just say, okay, I'm at a certain frequency and I'm sending wave into that, then exactly at that frequency, we'll measure what this thing is doing. Yeah? However, the understanding of a system will help you to guide to much more than what we know at this frequency. Yeah? And for example, this idea now is that there's some fundamental idea in nature which says a transistor has gain at one frequency. So can we learn, or do we know something about what will happen at another frequency? And the answer is this system approach we are just taking says yes, we can. So the idea is, when we know, for example, at some frequency what the gain is like, then for all transistors on this planet, in this universe, if you know the frequency at one, the gain at one frequency, then you will know also the gains at other frequencies. And this is totally different if you just used voltages and currents and you would just measure at this specific situation. Yeah? So this idea here takes you a lot further. Yeah? That's why we are doing this, because we can deduce from principles in nature the idea what will happen at some other frequencies. And now I have to say a little bit what we are looking at here. So when we look at such a transistor, you take essentially the same approach. So it's a cable, and what is then different if it's not a cable, if it's a transistor? What would you expect to happen when you have a transistor in between? Amplification, very good. Huh? The question is essentially how much, and also this is also a good point before we go into some details. What is the difference between a transistor and an amplifier? Maybe we can also take it from here, already considering this or what we learned so far.
The transistor only amplifies current, and amplifier also maybe the entire. I'm not sure.
No, this is good. It's a good starting point, but it's just there's a lot of things which you know already. We just have to order it. Yeah? Apparently, when you have a stereo or when you have some kind of component in your life, when, for example, your audio equipment has apparently an amplifier, it doesn't have a transistor. Yeah? And the reason why is that it's a fully blown system. What you just said, this is fully correct. I like the idea. If you have a transistor, whether this thing has voltage amplification or current amplification, you don't know, because it essentially means how you use it. And in the amplifier, you have something which is configured, while the transistor can still be made to something. Yeah? And if you express that in the terms that we are expressing, is that you say, when I'm buying an audio amplifier, I just plug specifically this cable in there, and then the system will do exactly what I'm proposing. If you have an open transistor, you don't essentially know how to connect it in a way that it will operate as an amplifier. That is the difference. So the transistor is, you could say, is the raw thing, and if you put a matching network or something around that, then you have an amplifier. Yeah. So the transistor is the center matrix, and you put some additional components around it to define these interfaces, yeah, to make it an amplifier. Very good. So apparently this concept, if you say it's too theoretical, yes, but maybe it's also useful. Yeah. And the problem we have with these system things is always that in the beginning you say, is the guy crazy? And I have to say in the beginning, yes. But the system which you are learning about is so powerful that you suddenly, with very much ease afterwards, can analyze very, very complex ideas. Yeah. So this reduction that we say, essentially whatever it is a matrix, which we are cutting down to the minimum knowledge, and then we connect it, and then we analyze. And then suddenly all the things pop up. Yeah? And for example, one thing which definitely will pop up is the idea that if I'm having certain components, like transistors, I will find certain things. And why is that? When we are deducing now, coming back to our original intention, so we look at this this derivation of a cable. So we said what we want to do is we have a cable and we want to maximize the throughput, or the what we later will call minimum loss or maximum gain. What can go wrong? We can say we have to do this matching at input and output, and we will see the central property. Yeah? In an active component, you do the same. You do it again. So you have a transistor at a certain frequency, and you ask yourself, if I'm doing that at a certain frequency, what can I get as a maximum? Yeah? And apparently there must be for a transistor something like equivalent of the loss at this frequency. This is then the gain. And this will pop in this mathematical derivation. And just look at the central line not to get confused. You're getting an equation for this maximum transition as a function of the matching at input and output, which has this structure. You're saying there's a gain, 10 dB, which I can mess up by matching. And if I'm optimizing it to the ideal matching at input and output, so making it kind of an amplifier, then I get this structure which has this central element, S21 by S12 magnitude. So it just comes out of the mathematical description. Now the question is, does this make any sense? And the answer is maybe. So again, a generator. You have your Netflix is transmitting. You want it amplified because on the load you expect losses. So the signal is going through at a certain frequency, going to the load, which will be effectively, hopefully, your receiver unit. Now, what would you expect to happen in this matrix? So there is a forward transmission, certainly. You put a signal, it's amplified and coming out. That's not really surprising. So there's something forward. With this matrix idea, which I'm going back to here, just a second, there's two components now. So the wave is influenced, of course, by the forward transmission. This is the S21, which is moving forward. This is the forward voltage gain. So apparently in an amplifier, if you put something to the input, you hope that something comes amplified at the output. What we often forget is that this is a kind of a matrix which also, you suddenly, at this load, you suddenly have a very huge signal. So let's talk to the messer. You have somebody speaking slowly into the microphone, 1,000 watt amplifier, puts it out to the people, everybody in Freiburg North listens. So you suddenly have a large power swinging at this matrix. You could say, okay, no problem. But from an electrical point of view, what do you get? You get suddenly look at this matrix from the output. So there's a huge wave at the output, which means that, of course, back through the system, there will also be an impact on the input. So when you have a large output signal, there's going to be a diminishing effect typically at the input. From an idea, why must this happen? Why can it not be that with electromagnetic waves we can exclude that a large output influences the input? Which phenomenon always tells us that this must happen? If I'm creating a wave here, can I stop it? I can diminish it, but I cannot stop it. Unless I really put some reflectors in there, but it's quite unusual. Yeah? So if I'm hoping that if I'm sending something into the signal in my system and it comes out here, how can I avoid that for some reason there's a feedback? In general, I have no certainty that I can avoid that. Yeah? So that means that if I'm putting forward an amplifier, it will do what is good. Yeah? But the idea is that this forward amplification is always, if the feedback is significant, then the signal will be diminished. And why is this now important? If you have a transistor, this parameter which pops up, which is this, has a defined property. It's not somehow happening in any way, but you learn from this. If you have this as a defining element, this is a property of the device itself. So this is these properties which you would select when you're buying a transistor. So you would say, I need a certain gain, so I'm going to a certain technology or a certain semiconductor, and this is now doing something for me. And I can either select one which has 10 dB or one has 20 dB or 30. This is really something you buy. You know? It's like a color. And then what you learn, and this is something which is then helpful in the understanding, is that wrong direction. That the property behind that, which we just extracted from the analysis that we are just trying to send power through the system, we are also getting some very unique properties. And we see that this behavior, and I'm just plotting it based on data only from a theoretical idea, that this property has some very unique features. And this feature is that the frequency dependence of a transistor is the same for all transistors in this universe. Which means, and what you learn from this behavior is that, first of all, what happens to the gain of a transistor in this sense over frequency? What would you say now? Does it go up? Does it go down? And if you, of course, the answer is on the table. The question is, why does this happen? So first of all, what does happen to a transistor gain or some amplifier gain over frequency apparently? Decreases. Yeah. First of all, before we talk about the numbers, why does it decrease? What are arguments in your life where you would say, this makes somehow sense? Can you explain that? This is good, but maybe explain it a little bit.
No, the impedance to the capacitor goes down, and that causes some effect. Like for example, in a volt, but if you have
Wow, that was the end of the discussion. I wonder what you just gave it. But before we come to that, it's correct. Thanks for that. But before we go to that, why would something which is amplifying not be constant, for example? How can we understand that? If you have a transistor, maybe from your personal understanding, what is a transistor? Transistor is, you said, capacitance. Why is there capacitance? Maybe to explain it.
The gate terminal low current flow is outside the tube.
Yeah. So when you have a field effect transistor, for example, let's start with that. There's always a gate to the channel. So there's apparently some capacitance forming. And how is this capacitance relative to the input?
When the frequency is up, the thickness depends on the thickness.
it's to ground, it's essentially a parallel capacitor. So you have the input signal and there's some to ground always a capacitance, because that's not something we can in any way avoid. Yeah? And you already gave the idea which defines this. In this sense, when you just look at the description of such a transistor, it always has a capacitor at the input. And you said the right word, it's a filter. And if you have seen in your life any filter theory, you learn something like the dependence of the frequency behavior depends on the order of the filter. And a transistor, in this sense, in a way is a low-pass filter. Yeah? And the slope, in this sense, is defined, because depending on how you did it in your preferred lecture, it's either 6 dB per octave or 10 dB per decade. Yeah? So not surprisingly, that the behavior of the filter comes down, the transmission factor. The same is true for the gain of a transistor. So you see the gain of a transistor comes down at a given slope. In a bipolar we have the same. So the bipolar is of course something, it's the same types of transistors. The difference is the principles are completely different, but what you can do is you can describe a bipolar transistor with the same representation, which is the parallel capacitance at the input. And if you know this, you don't have to know much more. The only thing you need is the value, but that's it. So that means that you can now invent any other transistor but is always describable with the same idea. So what you learn from that is that this transmission factor, or what we then call gain, of a transistor is extremely predictable. So if I know it has 40 dB of gain at 100 megahertz of frequency, I will know it has 30 dB at 1 gigahertz and 20 dB at 10 gigahertz. And that's why we do all this gymnastics, because this understanding of the principles will help us through this system. It is not that we have voltages and currents and we are completely lost about what we could do with this. As you said, when we have voltages and current, we have to discuss current gain and voltage gain and what is this. Let's go to something which we can easily interpret, and that is a very useful feature. So just as an example, if it's 40 dB at 100 megahertz, how much will it be at 10 kilohertz?
dB?
10 kilohertz, so 0.01 megahertz, so it's 3 decades. Yeah? So you would go 1, 2, 3, 1, 2, 3, plus 30, so 70. Yeah? And this is already something interesting, because then you go to 10, and if you go to 1 kilohertz, the same thing which we are now considering. So when we would speak about radio frequencies, 1 gigahertz maybe, 30 dB is okay, it's a factor of 1,000. But then we go to 1 kilohertz and suddenly it's 80 dB. A lot. Yeah? Which leads us to the next problem. So this is okay. We learned something. Because the description, when we represent things like transistors or any other features, waveguides by these elements, we get all kinds of frequency behaviors which we then can predict. There's one problem which I saw in your faces already when we discussed it, but nobody dared to say it, whether I'm crazy. And let me just go there again. I told you there's a gain. This maximum gain is S21 over S12. What happens if the feedback is 0? S12 is what's going back. What happens to the gain? Goes to infinity. And that is something which we have to look at, because there's one problem in this concept which is not really a problem, but which it needs inclusion now, which has to do with maximization of the transducer gain. And this is now something which can also happen, which by the way would happen also to the lady talking into this with a low noise into this very high powered amplifier, or the guy speaking very slowly. If it's a very highly amplifying device, this is one case when we speak very loud, very little. Yeah? If she starts speaking higher, and especially if the gain of the transistor is extremely high, what can happen at the messe when you are at the concert, which happens very only when they plug together the device? Which effect do we all hate when they are putting together these systems when we are early in the concert? So you're plugging in microphones and you're plugging in amplifiers, and it's not really well yet adjusted to the real levels. And then somebody walks with the microphone near to the loudspeaker. So in this sense, connecting the output very closely from here to the input. So the guy with the microphone will talk, there's an amplifier at maximum gain, maximum adjustment, and you walk with the microphone next to the loudspeaker. What happens?
Yes, cringing.
Yeah, cringing, and then also this feedback. Yeah, so this is something which we still have to consider. And what happens then? There's a feedback round which is critical. Yeah. The problem is now that, and this is something we have to clearly understand. First of all, where does the energy come from when we are in this situation? What is the input signal? Why is this, first of all, building a feedback loop at all? So there's nobody speaking, but you're walking with the microphone close to the loudspeaker. Why is there something, you said there's some cringing or whatever? There's some noise. Yeah, so that's something we have to attribute. There's always some noise which will create a signal. That's something we took from the beginning of the lecture. We said channel is limited in the presence of noise. Yeah? And that's helpful here, what might go wrong. So if there is a chance of feedback, this might happen. Yeah? And what is the problem which might occur? Why is then suddenly swinging up? There's apparently a condition where we are not aware that the system might go to a state where it's not linear anymore. Yeah, so apparently this very loud thing, which at some point is then limited by an electronic function, has to be avoided. Yeah. The reason why I'm speaking about this is we cannot really avoid that such a system, which is meant to be an amplifier, always is an amplifier. So what I'm trying to say is this experience from the concert, that this linear system, which is intended to be a nicely, very well-established amplifier system, apparently there are states which we have to guard against, that they are making suddenly go into a state where they are not working in the function which we ask it to be. The typical situation is the concert. Yeah? And let me explain that. What is the problem when we are considering a transistor in terms of mismatch? What could happen if we have very high gain and we have some kind of feedback? What can a system which is meant to be an amplifier system, what can it turn into? remember what we are designing here. So it could be not only an amplifier, it could be any system which has high-speed amplification, because it's a lot more than just an amplifier. But we start to with an amplifier to understand the issue. The idea which we have to guard against is that the system, and the reason is exactly what I was showing earlier in this plot. If this graph on the top level is true, it means that at some frequency, especially the lower ones, this system has an awful amount of gain. 70, 80, 90, 100 dB of gain, which means that any small signal will immediately be sent into a very high level. Yeah? So what must not happen that any signal enters this transistor uncontrolled. And now define uncontrolled. The definition is that we apparently in the system something is built in that the system starts to self-destabilize. Yeah? So we and the idea is when we look into that, it can happen that if we have some small input signal at some low frequencies will go through the transistor and feed back. And why will it feed back? Because the output signal is so outrageously high. So there's some kind of feedback either around the transistor or through the transistor. And then suddenly you have at some frequency you have an input signal which you didn't want to be there. And this excites the output again. Which means that something which you originally designed in a controlled way to be an amplifier starts to excite. And the reason I mentioned that, we have some very smart designers in the place where I work, and the first thing we are very afraid of is always you spend months and weeks and months on designing very high power systems, and then for the first time you put that together, and the first thing which happens, boom, the whole thing blows. Extreme overheating of the transistors, drawing a lot of current, much more than it is designed for. The whole thing just is a black hole. So it's very impressive when these things start to fly through the air, and thousands of euros just go through the pipe. And why can that happen is because at some frequency we always have some noise. We have a very high gain. This is entering, amplified. We don't want it to amplify at that frequency, goes back. And the idea is that this signal feeds back. Yeah, and the problem is that you can start thinking about that. What would be a stable condition? A stable condition is that that at any meaningful signal, the wave going into this transistor is bigger than the outcoming, which in some way implicitly avoids the situation I was talking about. In an amplifier, it's very controlled. You speak into the amplifier, and the maximum which is coming back is only what you send. This is the maximum which can come back. The same is true from the output. If you have amplified, a fraction of this can come back, but not more. The situation I was describing is opposite. Then suddenly from nothing, or from some other frequency, something can start blowing the transistor. So what we are saying in an amplifier, we have an implicit assumption that for the stability at this frequency, if I'm sending something into it, I can only get a reflection which is lower than what I'm sending, and the output can, what is going into the load, can only be what the transistor has, so to say, send out. There cannot be more. If there's more, this is very unhealthy, and it's not the situation for the amplifier. Yeah. And in this optimization, we already got a clue that this is possible, because I was showing you this maximum gain. And we are doing the same experiment for this, what that can happen to the transistor. You get this term. And when is this a unique number? If this parameter, whatever this k is, under the square root is a positive number. In this case, this will be a fine, well-defined amplifier. Then the idea is caught. If k is smaller than this, smaller than 1 in this case, then the situation is shaky. You don't know. This is the mathematical description of what I just described. You can say now, what on earth is he talking about? And what I'm trying to say is that when you are with a transistor, you have a couple of choices. You can self-activate the transistor by the matching. So apparently we are offering some impedances to the device. Yeah. Which normally would mean that there's a mismatch. Yeah. But there are certain parts of this ratio which are very unhealthy because we are kind of avoiding proper insertion of the energy into the transistor, which means that the device is intended to be an amplifier. It operates as an oscillator, yeah? Because you have no input signal, but you're getting a strong output, and that is a typical sign of the source, which is something we can build. It might actually be useful, but it's not what we intended to do. Yeah? And the point is, if you want to build an amplifier, you want to have an amplifier, not something else. Yeah? And that's why when we are critically looking at the analysis of this system, it's not only true for a transistor, it can be also something more complex, but the idea is the same. You are saying, when I have a gain, and the property of the transistor should be amplification, then this property, which we define with the MSG, is the maximum gain you can achieve as an amplifier. So this is something which is built in by nature. And it cannot be higher than that. Yeah? And when we are starting to think what could happen, to explain why I'm saying this, what could happen if I have, what is the gain of something like that if I have no input and some output? What would be the power gain of some system if there's no input? So I'm putting nothing in, I'm getting an output. What is the gain? Very simple. Something by zero? Infinity. Yeah? But when you start thinking about that, maybe that's useful, but in an amplifier system, this is totally not what I want. I want some input to be amplified. Yeah? So you start thinking, yeah, it's a bit crazy what he's talking about, but it may make some sense because the original intention is I want amplification, which means I have an input signal. Yeah? So there can be situations which might even be technically useful where there's no input signal, but if I want to describe the situation for some input signal at this frequency, then this plot says that in this case, if I'm doing it right, I get a maximum gain of 30 dB at 1 gigahertz, not more. And this is helpful because when you do things in reality, so for example, I'm building buying a transistor, in this case from NXP, so this is a transistor, and I'm just doing it by experiment. So I'm putting tuners to the input and I'm saying I can offer all the impedances which are possible at this frequency. I can do that. It will be a very costly experiment, yeah, because I should know what I can expect. For example, if this thing, by definition, if it's this transistor, it has, let's say, an MSG of 30 dB, and I should watch that I'm staying in this region. If I'm finding suddenly a gain which is higher, and I can get that, why? Because I can create an instability. I'm avoiding the input signal in a way that there's no proper transmission anymore. Suddenly I'm getting 40 dB in the measurement, then I know this is false because the invariant says this transistor only has as an amplifier 30 dB. And if I'm measuring 40, then I'm at the verge of an explosion because I'm on the way to build an oscillator already. 40, 50, and then you just tune, and suddenly either boom or you have some controlled oscillation if you build it in a way that this transistor can support that oscillation. So that is the problem in this. You could say, no, this is a crazy problem from some radio engineer who doesn't know what to do. Okay, I would accept that. But think back what the problem might be for your latch in a digital thing. So you go back to your microprocessor. In a microprocessor, you have the same situation. You want to send a signal through the system to go into the memory. Now, if in anything of the chip which we started with, and that's why I'm saying you we need this. This is a million transistors. Now you are cooperating, and you have to see how this is designed. So at some point, all the data we have collected in this room is put together in one chip. And now some of you in the background has not done this stability analysis correctly. So at some point of the chip, some function doesn't work. It's oscillating at some frequency where we didn't look. Which means that the whole digital, and be it digital or analog function, just what has to be involved is has to be some kind of, if amplification is possible at some frequency, and we haven't guarded against this problem, then the whole system will be completely useless. Because what you cannot do is just say, okay, we exchanged the lower right part. This is integrated. So this is not something we can just trial and error. We need this analysis before we do that. Because otherwise the function which you are designing, and it's not necessarily just amplification, anything which is active can have that problem. So this is these things we need on the system side to design something useful. So in this sense, we need some mathematical description which helps us to build what we want. And in this sense, just to tell you what if you take it in a nutshell, so you take some transistor, be it from a real component you buy, or you take some active switch in some integrated circuit or some memory component, and you make that analysis because you connected it. And then you're sending this analysis, which I just showed you, over this device, over frequency, and you're realizing this seems to be okay. Then you are in good shape. If you see some spikes or some predictions that the gain of this buffer or whatever you're creating is higher than what is predicted, be very careful. Design on it and prepare yourself to do that. And what you're getting with this is that you're using some laws of nature or some basic principles to help you. This is the idea of system design. It's not that you just measure something crazy and put it together, but you say, if this thing at some frequency is analyzed, then it cannot have more gain than that. And this principle is so useful that you can design yourself through that and can make the appropriate selections. And that's number one, what you intended to do. But the other thing is also, if you're very focused on what you want to do. So this cell phone is 2 gigahertz. So I'm just looking at 2 gigahertz. And then what you learn is, of course, this is nice. But this thing has all kinds of properties based on this. This at 10 kilohertz will have 80 dB of gain. And then you scratch your head, what is this? What is it really predicted to do at 10 kilohertz? And then you can say, okay, let's look, make this analysis, simulate it, and see what you get. And if it has some risky behavior, suppress that. And then you can design a system in advance which does what you want to do. Good. This is the first part where we're making use of that. What I'm trying to imply is here, that's the only thing why I'm doing this complex stuff, is that you understand that you're being given advice what to do, looking from the right perspective. Yeah? That's the idea. And now you can lay back and say, okay, every transistor on this planet, that's the left part. Yeah? On the right, we have to talk. At higher frequencies, there's a second effect coming up, which makes our life even a bit easier. Yeah? So in this fraction of the transistor is because the power degrades at higher frequency, the ability to amplify. So it doesn't go on like that. There's a second thing. So the only thing you learn at this part is here that there's a limit for this problem which I described. So at some point, because gain is coming down, the ability to self-activate will go down, and at some point it simply vanishes. Yeah, so you don't find an impedance anymore where this goes bad. And then the transistor is only an amplifier. It will not uncontrolled go back to an oscillator. I promise that's what this says. But you have to accept the idea that something can be different than what it was planned to do. That's what you catch from this lecture. You know? And it's unique. Anything you do in electronics will obey these laws. So that's... Pooh! It's always tough to understand that in the first place, but what I'm promising is once you have these tools, you're very powerful. You can do things which you didn't anticipate. And what is it now? iPhone 14? So for iPhone 14, what is it? 10 billion transistors? This analysis has been done 10 billion times. So, and it is in place. You can buy it for Christmas or for the holiday season. And you see, this is very predictive and useful that you can get yourself through that, and it's working, so you can really do that. It's not just theory. It's really real. Yeah? Otherwise, these things would never be developed within 6 months. Yeah? I hope it's attractive, and you're at universities to study exactly that. Yeah? So not just plug together some cables. This is something everybody can do, but you start to understand that the principles behind that get you far away into the future. Yeah? And what I like about it, we cooperate. So I'm going back to my colleagues. We are 100 designers working on this stuff at EIF in a way, and we always talk in this way, directly and indirectly. It's a very nice way to live in. Very trustful, by the way. So I trust everybody I'm talking to. I trust the person to give that analysis, and he will trust me or she will trust me. It's very nice. So it's a good way. So sorry for being over time, but I hope this is now understandable. Next thing will be something even more interesting. This is very theoretical. Next time we will come to some real applications based on that. Yeah? So we can use these things we are now found out to build something like GPS. So just to give you an idea where we are going. Yeah? These are the fundamentals also to do something as useful that where are you on this planet is just based on exactly the same ideas. Yeah? Thank you very much and see you next week.